Okay, so welcome back. We're at homeostasis. This whole semester we're going to bounce back to homeostasis. And homeostasis in body tissues requires that our cardiovascular system be able to adjust the pressure and the resistance um, in an effort to maintain adequate blood flow to vital organs at all times. And by adequate blood flow, we don't just mean having enough blood get there, but we also mean not having too much pressure reach a certain tissue so that we're going to damage the capillary beds or the vasculature that's there. There is a very lovely and somewhat intimidating when you first look at it feedback loop for autoregulation. And here it is. It's autoregulation, the big picture. It's out of your textbook. What we're looking at here is we're looking at how the body autoregulates blood pressure, blood flow. There's this complex interplay that's going to work with everything from the baroreceptors through the control centers, in the bloodstream, in the hypothalamus and pituitary, to the cardiovascular center in the medulla, all of that. So we're going to have this complex interplay between vascular, nervous, endocrine, all of these organ systems like the adrenal glands, the kidneys, and the heart. And really what we're looking at is how we're going to regulate blood pressure. So certainly go back. This is in your notes. It's in your PowerPoint presentation. Just go back and take a look at it. I believe it shows up again a little bit later and we'll run through it. But before we get there, before we get into this whole big picture, I want to go and I want to pick up some little pieces because I think if we do that, I can actually come back and look at the big picture as a whole, and it will make just a little bit more sense if you understand some of the smaller players as we go through. So, vascular autoregulation. So we need to talk about how the vascular system senses alterations of the blood pressure and the blood flow, and signals in the cardiovascular centers in the brain, and then what it does about it. So essentially what needs to happen is that the heart needs to modify its rate and force of contraction in response to these alterations that are being detected. This can happen all the way down to the arterioles and the precapillary sphincters that we spoke about at the medarterials, just so that we can adjust resistance at a specific tissue bed. So let's take an example. For example, during an emergency, the autonomic nervous system will cause dilation of the precapillary sphincters of the medarterioles, right? Why? Because we're in an emergency situation. We need to get more blood into those skeletal muscles, more blood into the lungs, more blood to the brain. And so to do that, what's going to happen is we're going to start constricting the precapillary sphincters found in tissues that aren't those. Tissues like the skin, like the GI tract, like the kidneys, tissues that can have a little less blood flow in this emergent situation so that we can get more blood to those vital organs that need to deal with whatever this emergency is. What's going to happen is we're going to send the majority of the cardiac output, the blood flow, to those flight or fight response organs. And in the process, because we're doing that, we are in truth depriving, if only temporarily, we're depriving the non-essential emergent organisms through a process of vasoconstriction. So vascular autoregulation is going to just allow us to redistribute where we're sending the majority of the blood. We're not going to cut off tissues entirely. We're just going to deprive them a little bit for a short period of time while we deal with whatever emergency is going on. The cardiovascular center is going to play a role in autoregulation as well. Remember, we talked about the cardiovascular center and the medulla oblongata. We talked about some very specific neurons. Specifically, I think we talked about some parasympathetic fibers from the vagus nerve. We talked about that cardiac accelerator center, those nerves that were sympathetic in nature, as well as the vasomotor nerves that were sympathetic. So remember back that we had some baroreceptors, right? And we had some baroreceptors in the aorta and the carotid bodies. But what we also have is we have chemoreceptors. So we have chemoreceptors that are also found in those carotid bodies and the aortic bodies, and these chemoreceptors are very close in proximity to the baroreceptors that we spoke of before. What these chemoreceptors do is they're chemical sensors, right? So they're going to detect things like hypoxia, which is, remember hypoxia, Hypoxia, hypoxia is low blood oxygen. Or they're going to detect hypercapnia, which is a high CO2 level, or even acidosis, where we have excess hydrogen ions. And what these chemoreceptors are going to then do is signal the cardiovascular center. In so doing, we're going to see an increase in sympathetic stimulation. We're going to see an increase in heart rate and respiratory rate. We're going to see vasoconstriction of the vessels all the way from arterioles to veins. And what that's going to do is it's going to increase that blood pressure. So we've got this cardiovascular center that's going to play a significant role as well. This talks about those baroreceptors that we've mentioned before. They're two of the most important control points are pressure receptors. These pressure receptors that we call baroreceptors, again, we've mentioned repeatedly that they're in the aorta and the carotid sinus. We also have baroreceptors in the kidney and in the walls of the heart. What we're seeing though here is just is stimulation of the baroreceptors. So what they're picking up is an increased pressure, and that increased pressure, say in the carotid sinus, we're going to call that a carotid sinus reflex. What the carotid sinus reflex does is it helps to normalize blood pressure to the brain. We don't want to that's a bad way to say that. We don't want to send blood pressure that's too high to the brain and risk damaging those vessels or those tissues. By the same token, we don't want that pressure to be too low and actually not get the nutrient, the oxygen, to the brain that it needs. So stimulation of aortic baroreceptors will help normalize systemic blood pressure. So the carotid sinus baroreceptors will help influence blood pressure to the brain, whereas those in the baroreceptors in the aorta are going to normalize the systemic blood pressure. In those aortic baroreceptors, what we're going to see is that when blood pressure drops, the baroreceptors are actually going to stretch less. These are basically stretch receptors. And so what happens is when we're stretched less, we have an input, we send nerve impulse to the cardiovascular center. It's going to respond with a decrease in parasympathetic and increase in sympathetic stimulation, and we're just going to see blood pressure increase and go back up. Here's your slide on chemoreceptors. Chemoreceptors in the carotid bodies and aortic, very close to the baroreceptors. Remember what we said, they were going to detect levels of hypoxia, hypercapnia, acidosis. They were going to result in the stimulation of the cardiovascular center, an increase in sympathetic stimulation to the arterioles and veins. These chemoreceptors also will affect respiratory rates as well. They'll play back on the respiratory centers in the brain as well. Okay, so that's where we're going to break on this one. We'll pick up with neural regulation of blood pressure, and then we'll talk about the different types of syncope in our next video.